Hello, welcome to episode 16 of the 4coder Lexing project. We're doing code gen today, like actual generating C code. We're generating it off of the state machine model that we've been optimizing for basically all the previous episodes, save for the last one. And yeah, so we have down here an example that we wrote last time of kind of what this is going to look like, although this has a bunch of features that we're not actually trying to implement. So what we're going to implement is basically going to look like this. Each state is going to have one of these little blocks. These blocks will have a label so you can jump into them, and then handlers, and then at the end we exit. At the top we'll do this, and we'll have to along the way do some other stuff, generate maybe help or handwrite maybe some helper code that these can call into, so that like when we're doing things like the keyword lookup stuff, that'll need to get resolved. We'll probably need to, at some point in the next episode or two, probably not this episode, but sooner or later, we're going to be looking at generating keyword tables, basically hard-coded hash tables, compiled time hashed tables that we can do some fun hash table stuff there, picking the specific hash function that avoids the most collisions. Just for an example. Yeah, there's a lot of fun stuff we can do. So, for now, I just want to jump straight into the meat of this. So, what we're going to do is we're going to write gen functions. And the main gen function is just going to get plopped down right here, and it's going to be called gen control flow fast control flow. Those are the features I want, and here's the context I want you to generate off of. And then I'm also going to pass down the standard out. This is so that I can abstract away where the output is being written to, so that when I'm ready I can start sending this to a file instead of to standard out. But for now I'm sending it to standard out so that we can inspect it in 4coder sort of as it's being built up, and once it looks like it's ready to go to a file directly, we'll build up some stuff around this that gets the right file handle, right? And that way all the control flow generating code doesn't have to be rewritten later. Okay, so the first thing we want to do is we want to do a little bit of work to figure out what the names of things are going to be and stuff like that. I said down here that the inputs are a token list and the signature is a token list. This name we have to figure out, and then these inputs here. So let's just write that. All right, we gotta get into the habit of printfing now. We're printing out a token list returner. I'm going to have it spit out static there. I'll try to avoid using too many of the well, no, it's got to build in the 4coder code base. Let's say that. I don't know. It'd be kind of handy to have this work everywhere, so we'll say it does not have to build in the 4coder code base. I mean, while we're adding features, we might as well do that, because that one's almost free. You know what? That's wrong, because it's going to use a lot of things like arenas and stuff, so it is tied to the 4coder code base. Now, instead of calling path, I'm going to call it full input control flow. So full input is the way that I want this thing to be called. So this is going to be Lex full input, and then the language has got to be C++, and arena input, right? So there we go. We have our function body there. We can say we're going to build this list. I'll call it list. Or something like that. And there we go. So if we just ran this, what I would get, well, first of all, I want to take out my debug prints, right? So my debug prints have been kind of guiding us all along, but they're going to get in the way of us inspecting the code we're generating now. So let's take a look. There we go. So far there's nothing parameterized about that. No matter what state model I put in there, that's what I would get. But that's actually not correct. It's already wrong. because I've hand-coded that CPP, and I want this to potentially be used to build other language parsers rapidly once I have finished it. So what I've done is I've said before you include LexGen main, there's a part of the model that you define before you include it so that it can define all of its code based on those macros. And this is one of those situations. So what I want to do is I want to say this needs to become, let's come up here, and we're going to define lang name lower string as the thing you get when you stringify. I think I have this. Stringify, come on, stringify. Did I just call it stir? I have to figure out what I called it, but when you get the stringed version of that macro there, lang name camel string, those when you get that. Now let's go look at the base types of 4coder. Do I have a string macro? I have a stringify lowercase, that's what it's called. Stringify. So stringify just takes a macro, expands it, and then passes that expansion to another thing that stringifies it, right? Classic macro nonsense. With that, what we can do is up here where we directly put in the CPP, we can now say that's not actually what happens. What actually happens is we use the lang name lower stir, like so, right? Yeah, that's fine. Everything else here I think is fine. And that looks good. So if I needed to change the language name, I could go to the CPP file and say that this is actually called C, right? And now Lex full input C, right? So that gives me the ability to define language name stuff. So that's handy. That's handy. The next thing we're going to want to do is go ahead and generate all of this state structure stuff, right? So gen full input state control blah 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 blah. Let me look at that side by side with this. So things we need before we do that, we do want to grab those pointers. So let's do that. So we're going to have a putter that starts at the input string. It's going to iterate to the one past last position, which is right there. And once we've got those, then we're ready to, we don't need buffer space because that's only for buffering up in values of the source that might get lost over temporally chunked input, and we're doing full I'm going to call this fully contiguous input. Gen contiguous control flow Lexer. There we go. Okay, so we have those. Once we have those, the next step is the state blocks. So we're going to do a loop over the states. That's good because we've done that many times and we know what that looks like. Go, loop over each state. We don't need to loop over the transitions yet. For each state, we need a block, all for that state, just to keep things organized. Technically, the generated code wouldn't necessarily need this, but it might make our lives harder. We'd probably have to pull things up here. Maybe eventually we'll do that if we feel like it makes the code more optimal for some reason. But I don't think that we care. I think that the C++ optimizer will do a fine job with what we're going for here. So the next thing we're going to have is we're going to start encountering situations where we have names that we want to convert into unique identifiers in the C++ generated code, but that either aren't valid identifiers or aren't unique on our side, and we need some way to make them so, right? So this is the first case of that. So if I come over here and I look at state, state has a pretty name. Well, I'm going to need to extend that to have also have a So we have a couple of options. We could go ahead and say that we want to have a identifier name. But if we do that, what we're going to now have to do is every time we visit a state, we're going to have to have a thing that sets the identifier name for every state. So what are pros and cons to that? Pros are when we generate the generated code, we'll be able to look more human, if you will. But the con is that it's a lot more work to generate. So what can we do to bridge the gap there, make it easy to generate, and keep it within range for humans to understand? Well, we don't really actually care if this code looks like it was written by a human. We only care if a human can inspect it and debug it. So we don't actually need an identifier name. We still need the pretty name, but we can use the pretty name without using it as an identifier. What we have done is we've given every state its own unique number, right? So do I have a thing down here that makes sure... I'm going to move this to somewhere else because it keeps annoying me now. Lexer Generator. Something like... control flow examples.cpp. There we go. Okay. More importantly, when we're in here, when do we ever set the numbers of things? So flag set numbers is a thing, and that's the only one we do. So we want to do a states set numbers. And states set numbers needs to be a loop over states. So good thing we know how to do that. We've done it many times. Loop over the states. For each state, assign it a number. I'll have the numbers begin at 1, just because, I think. Do I want the states to begin at 1? The advantage to having them begin at 1 is that I reserve 0 for an error state, but I'm not actually generating an enum of states right now, so I'm not sure that that's relevant. But it doesn't hurt, and it doesn't matter, so I might as well do it this way so that this will work when I go to make enums, because I'll probably want to do enums at some point for states when I want to do like resumables, and then I'll want this to be at 1, and I don't want alternatives anyway, so this is where we're going to do it. This is the way we're going to do it. Yeah, we need the optimizer to set all of the state numbers right here after it's done optimizing, right? And so I want to put in a separator here. So this is high-level optimization. Debug inspection of model code generation, right? Keep things organized. Up here we're going to put type checking if we get around to implementing that ever, which hopefully we will, because it's pretty important if we're going to actually like let other people use this and stuff, right? Anyway, contiguous control flow Lexer. So you now can rely on each state to have a number assigned to it. So your label can just be this. State %d, call you state label %d, boom, boom. And then what we can do is stick the pretty name right here so that it's a little bit human understandable what's going on still. So state label %d, the d comes from the state's number, and the pretty name comes from the state's pretty name, right? So that would give us this. Close. We need a new line after that. Close, but we don't want a new line there. There we go. So now we have some initialization code, and then we have these braces going through here, giving us each state a scope. We can see that we have 65 states, and except for the things where the generated states don't have very useful pretty names, everything else is identifiable. We could actually give the op states prettier names if we wanted to work on that, but it doesn't feel worth it to me anyway. So yeah, these are the states that have survived optimization and that are participating in the actual state machine we're generating. Cool, huh? So far what this does is it generates initializes some pointers, and then it labels the same position over and over and over and over again, none of which actually accomplishes anything, and then it returns a zeroed list. So, not actually doing anything yet. Let's see what we need to do next. So our examples says that one of these blocks here needs to do some stuff here about checking if it's at the end of the file. So that's our first check, is no matter what else has to be done, we need to know if we're consuming an end of file state. The end of file state basically isn't coming in as a character in our setup. It's coming in as this check if the pointer is at the one past last position, right? Now, there's, a possibility that what we would actually want to do is, since we're getting the full input handed to us anyway, reserve a character that is like the end of file character, and when we detect that, just treat that as our end of file indication. Problem is, I kind of want to be able to handle every possible character that shows up without being fooled into thinking that's a terminator, right? I just want to be able to say, here's a blob of data, treat this as a file, and it doesn't matter where you see null terminators or end of files or any other kinds of weird characters, just lex this section of data no matter what. Because otherwise you end up with weird 4coder bugs where the Lexer just stops in the middle and it looks weird, and I've always hated that. So I'm going for a new model where every character, 0 through 255, is not an end of the stream, and the end of the stream is a separate event from the 256 possible byte values. And since I don't want to represent all of these as 16 bits, we're just going to do that as a control flow check, especially since we're not even using lookup tables for any of this, right? The lookup table one would probably want a specialized thing that does this very differently. But that whole system is driven and it is structured very differently, so we don't need to spend any more time dwelling on how that system looks. For now, we'll just generate the code for how this system needs to look. So, if the, let's see, if the putter if the putter equals the one past last putter, we have some work to do. So I'm going to stick this inside a block so that we remember that it's all basically so I can remember what the nesting of my blocks is. So this block is inside the for loops block. This new if block is inside this, so I can see the actual nesting of the generated code in my generator code, right? Interestingly enough, the actual generated code won't have any nesting, but conceptually I want to think of it as if it has nesting. Okay, so the generated code now is going to check if we're in that situation. The last thing that we'll always do is, if we saw that, we want to go to end, right? It doesn't matter where the handler says it wants to go, because all that handler transition is actually saying is, this is where I would go, like, if it made sense to go somewhere, but I know that this is the last step anyway. So the next state will never happen, right? At least if it does, it's an error. Maybe there's another argument to be made there that there should be an error state, but that would only make sense if we were trying to do a resumable thing so that we could check if we're in the error state. In this case, all we have to do is, when we reach the end, we're assuming we have the full contiguous input. So when we reach the end, that's the end. We're done. We're never going to do any more lexing on this particular file. Okay, the last of what we have to do is we don't have to do this last chunk stuff, because that's for if we're doing chunks. What we do have to do is figure out what else needs to happen besides going to end in the case handler, like what actions happen before the transition, basically, right? So let's come over here to our state transition. So we are saying, okay, first we want to know what's the condition, what transition handles end of file. Now that's not actually a straightforward question to answer because there could be more than one transition that handles end of file given the state of the flags. So we can't actually answer that yet, but maybe we don't want to. Maybe what we want to do is say that we're not handling actions yet, and we're not handling emitting is a type of action. So we're not handling actions yet. We're only going to handle the transition rules, right? And we'll then go back through and do another pass that figures out how to do the actions for consume, the actions for emit a token, the actions for setting a flag, and the actions for updating the delimiter positions, right? So all of that will happen at another time. For now, what we want to do is just say that that's not implemented yet, and move on. Okay, so we can check if we have the end of file, but we don't know like what transition handlers are relevant to that situation. The next thing we want to do is work out, okay, if we iterate the transitions and figure out how to organize them, and maybe this is actually a case of we've written this down too soon, or rather writing this down has led us to handle a more basic problem that's going to cause us to do this differently. Because this always does need to go first. We don't want to be reading from the putter if it's past the end, if it's one past the last spot where the putter is valid. But that is actually a case, right? That is a transition handler. So what we kind of need to do is we need to look at all of our transitions, and we need to say, can you sort yourself in such a way that we can iterate you once and output you in the correct order? So there's a couple of things we want to do when we go to sort those. One thing we want to think about is the transition order should always put its end of file handler first. But one thing we haven't done is made sure that the end of file handlers are all separated out from everything else. So maybe the right first thing to do is to say any transition that has an end of file input as its condition set needs to be split into two transitions that has that twice, right? And then the second thing we need to do is when we go to sort it, make sure all of those end up at the top, and then make sure that the one of two things needs to go at the bottom, and everything else in the middle doesn't matter as much. Although there might be some reasons for optimization's purpose to prefer certain orders, so we would have to figure that out on a sort of more case-by-case basis later on once we have more of this working. But the parts that we know we want to consider pretty early on are what goes first and last, because what goes last gets two cool benefits. One of those cool benefits is that if it has a lot of possible, like if the thing that goes last is triggered by a lot of possible inputs, then we get the freebie of not having to actually test for all those inputs. So if it's fairly costly to test for all those inputs, but we put it last, it becomes the fallback. It becomes the thing that happens no matter what, because if we reach it, because none of the other tests have caught it, right? And we never want to have something that, like a state that isn't going to operate on its input. So we get to say that the last thing doesn't actually check to see if the current state matches the condition it's supposed to be in, because all of the possible states are covered by one of the handlers, and the last handler must catch everything that wasn't already caught, right? So we don't have to test anything in the last handler. Second benefit we get is that we don't have to do a goto if the last handler goes to a state that is the next state in order. So there's also going to be an argument later on about how we want to sort states so that things can take advantage of that as much as possible. So to consider all of that at once is going to be too much. What we want to do is we want to say, let's start with these two principles. We need to separate out the end of file conditions from everything else, and then we need to sort those to the top. And once we've done that, we need to, that's thing one, and then once we've done that, thing two is we need to iterate the transitions and just generate them the big, dumb, sloppy way. And then we'll figure out how to shave off some of the slop later, right? Yeah, that's how we want to do it. There's also things we want to think about, like optimizing how we do checks and stuff, and all of that is going to influence this, because if we have some state conditions that we want to test, knowing how expensive those tests for those conditions are will actually influence which ones want to get that default handler position at the bottom. So we can't even really answer the question about how to sort things to the bottom until we know how hard it is to test for them in the first place. So there's different details to work out one at a time. The first details to work out are, can we just get the structure correct? So we need to have the end of file first. Our code would be incorrect if we didn't do that part. Optimizations will have to come later. Okay, so that's enough thinking about that. It's time to actually do something about it. So we have two ways we can do this. The quick, dirty way would be to say, loop through all the transitions and find the ones that do things during end of file and implement that portion of the transitions here, and then loop through them again and output everything else here. The other one would be to say, let's do some transition splitting and convert any transition that contains this condition into a separate transition, and then do transition sorting. Pros and cons of each. One, the second option is probably where we're going to end up eventually anyway, because we're going to want to end up sorting these transitions by a lot of factors, and having the ability to just break them down into smaller atoms so that we can sub-sort things will make our lives easier. Since that's where we're probably going to end up, it makes some sense to go ahead and just get that done now, because we know we're going to end up there. We know we won't be wasting our time to implement that, but it is a little bit heavyweight for the current situation. We could get other stuff going faster if we didn't spend time on that now. And it might turn out that we never actually do those optimizations. So even though we want to do that pretty much as soon as we start optimizing transition handling, this might not be the structure we end up wanting for our state machine anyway, in which case we won't use that. So there's a slight chance that we won't go far enough down this road to actually get that payoff, I suppose. I think that one way or the other we're going to want to start manipulating the model again at the low level, basically making changes that are specific to what Lexer we're doing. So it's time to just go ahead and say, alright, if we know how we're going to be generating code off of the model, that influences stuff we want to do next, but we don't want to change the model if we're going to generate stuff off of this one and generate stuff off of another one, right? Or to put it another way, if we're going to generate several different implementations, the high-level model needs to stay intact, because the low-level optimizations we apply might not be universally helpful in every case, right? So we kind of want to be able to say copy the entire model at this point. So maybe that's where we should start, is say, look, we're going to start applying low-level optimizations. Low-level optimizations are low-level in the sense that they only help us get closer to good code when they are applied in conjunction with the knowledge of what type of implementation we're generating. High-level optimizations were helpful no matter what, and these optimizations not so much. We're going to start doing things like transition splitting for special cases, sorting transitions based on what's important to them and stuff like that, and none of those changes would make any sense in a lookup table or in several other things we might end up doing. Like if we try to do isolations of the state machine to do small lookup tables within a hybrid system, right? So I think that's where we start. Is we want to be able to copy an entire model. So we have the ability to copy various different things. I want to see copy action list. Do I have other things called copy? I know I have other things called copy. Yeah, here they are. So copy action list considers itself a part of the optimization section, whereas these other copies for field manipulation consider themselves part of the SMI section, but these also get used during construction, which is why. So I think this is an optimization section thing. We're going to go ahead and say that this just lives right here. So when we copy a model, first thing we need to know is what things about a model are unique when we copy them and which things aren't. And I think the answer is that the flags, the state list, and the root are the things that we are going to manipulate. The tokens aren't really going to change. That's actually more of like, it is what it is. It's very clearly defined one-to-one relationship type thing. The flags probably won't change, but there might be some stuff that happens in terms of sorting the flags into specific orders that will become dependent on particular optimization strategies. The roots probably will never change, but we do kind of want to think about what if we actually did have a situation where we optimized out the root and needed to change the root pointer. So I think what we want to do is, say that there's this idea of a Lexer model that contains these things, and then we're going to pay a quick price on making that organizational change when we have to stick a model dot everywhere. Next. Oops. Yeah, you're not a thing yet. What else you got? Yep. 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 Okay. Alright, so now what we have is a nice way to separate out the primary context, which has like our memory allocation primitives, and this part of the model, which is a little bit distinct, as this isn't really about the code generation as much as it's about the type generation. Like, this is about, this model here it's the state machine that represents the runtime logic, right? It encodes the algorithm of the parse, whereas this kind of encodes the data structure that is being generated by the parse. And those models are actually pretty separable because we don't want the data model to change at all when we go to use different optimization strategies. So there's, pretty good reason, I think, to think of them as separate models, with this model being kind of more fundamental as it's the thing that defines our data interface, and this model being the thing that defines like how we generate data from other data. It's basically our code, our data transformation description, and we can do a lot of work on optimizing that, where there's not really anything we can do to change this because it just is what it is, right? The only reason it's even done here and not in handwritten code is essentially because there's a few places where we can make it easier for the user to do that, to specify it by operators and stuff. being automatically handled a little bit more simply than they otherwise would be. And by linking certain things together, like since we want to be able to tell which keywords go to which token types, having them handwrite that in such a way that they specify new tokens with the lexemes that go with them lets them specify all these things once, and we just save the results of the set of tokens they actually specify sort of in the background for them, rather than having them just handwrite out a list and then do the linkage as a separate thing. So, it's essentially not a part of the model, is my argument. Copy model. So here's the goal. We want to be able to completely copy an entire Lexer model. So what has to happen to do that is the following. We need to be able to copy a flag set. Can I do that? Flag set. I can't copy a flag set yet. So we're going to call this result. Result.flags equals opt copy flag set arena models flags. So we got to be able to copy the flags. I doubt we can copy an array of states, so we're going to have to ask for that too. Result. Let me just copy states. State. There's too many things that there's pretty much no chance that you can copy states though. Did I never remove all this code here? Yeah, this is the old set code. Don't need this anymore. Field pin, field. So this is the condition set stuff. We have copies for that. Input set copy, condition node copy, condition set copy, condition set copy, push string copy, and I think, okay, offset has a copy. Yeah. So that kind of determines it then. We're going to need this as a part of the copying stuff up here. That pretty much determines it, though. There is no way to copy states yet, so the new states needs to get generated by opt copy state set arena models states. Then finally we need a way to set the root, and the way we'll have to do that is we're going to do a loop over the states. I'll call this state equals model.first. New state equals result states first. States first. None of these should reach 0 before we find what we're looking for. And they should exist in the exact same order. So we can just rely on parallel iteration to get us what we need. If the model's root equals the state we're looking at, then the new model's root equals the new state we're looking at. Break. And here we're just going to assert that we actually found a new root for this thing. Okay, just to be sure. So that leaves us with just a couple of jobs. We need to be able to copy a flag set. So that looks like this. Now, do I have the ability to copy a transition? I think I do, but not necessarily wrapped up in one spot. I think that I have the ability to copy everything inside of a transition, though. I can copy a condition pretty easily. I can copy an action list. So yeah, we'll be able to copy transitions. States, they're not going to be allowed to have on-entry actions by the time we go to copy them. We can copy their transition. We can copy their pretty name. We'll zero out their back references because that's just a thing we store on them. So yeah, this stuff will just zero out. The number will copy, I guess. We don't even really need to do that. This will get zeroed all of this out. And that's stuff that we use to store information on states sort of as we're operating on them. This is sort of to support like optimization algorithms and stuff. This we want to just keep it the way it is. This is a part of the original model that doesn't actually survive the initial optimizations. So their real structure is kind of like this. This is throwaway. This is fundamentally important, and these are non-copied, but they will be used later. So I'm going to keep them ordered like that. And so now we go ahead and say, how do we copy a flag set? Well, a flag set's just a linked list of flags, so this is a fairly straightforward thing to copy. We're going to visit each flag. For each flag, we're going to create a new flag. Again, let's see about these. So reset rules are part of the actual behavior. Token base kind. What does that have to do with flag? I forget what that does. Ah, that lets us bind, I see. So problem is this says token-based kind and not token-based flag. So these are fundamental. They're about how these flags get translated into token flags on the output side, and then these are for operations during optimization. So these don't get copied, these do get copied, and none of these are deep copies, so everything's good. We create a new flag, we're going to push the new flag onto this list. We're going to copy those fields, and there we go. So that's a copy flag set. Now we just need to be able to copy a state set, and we're done, right? No big deal. Except that this probably will take the rest of this episode, honestly. It's pretty deep copy. Copy state set. Arena. State set. Result. This is going to look just like this. So I'm just going to do that. Flags become states. Little flags become little states. And then finally, the new state itself doesn't actually get generated this way at all. The new state needs to get filled by doing opt copy state. And this is where things start to get pretty confusing, because we can't actually just copy transitions either, right? What we're actually going to have to do is make a lookup table that goes from old states to new states, and then use that to copy the transitions later. So this is wrong. This is all wrong. I mean, it's not all wrong. It's just going to get complicated. Here we go. So we're going to need a table. Table U64 to U64. Old to new. Probably want it new to old as well. If we don't, we'll get rid of it later. Make table U64 U64 on the base allocator of our arena. U64. The number of slots you're going to need is the number of states times 2. At the end of all this, you'll be free to release your tables. So table free, old to new, new to old. How do you feel about that so far? Allocator, do you need me to call it base allocator? Table free, do you need me to pass you a pointer? There we go. Now every time I create one of these, what I need to do is table insert, old to new, U60 for putter as int, and then new to old. So old to new means I take the old state and I take a pointer to the new state. And going the other way, I take the new state and take a pointer to the old state. So there we go, we made the lookup table. Now, is there anything in here that I can save? The pretty name. The pretty name we can get right now. That can just get copied. Pretty name equals push string copy onto our arena of the state's original pretty name. Okay. So we now copied this and this. The rest of it is left as zeros, as it should be, so the only thing left is the transition set. Now the transition set itself is actually, or the transition list itself is actually going to be the hard part. That's why we needed these tables, because we have states. Each of these states has a list of transitions, right? So one state, list of transitions. Each of those transitions can have pointers to any of the other states, including pointers back to itself, pointers to states we haven't seen yet, pointers to states we have already seen. All of it is on the table. So, because of that, what we really need to do is say, build this table, which we've done, and now we're going to iterate all the old states again, and what we could do is iterate the new states, and for each new state, look up the old state that goes with it, and iterate the old state's transitions to copy those transitions, and then every time we look at a transition, we need to use the old to new table to turn parent state and destination state. Well, at least destination state. Parent state we can just derive from the fact that we know what state we're filling in. But destination state we need to fill by looking into the table to turn the old state pointer into a new state pointer and link things up correctly, right? While we're at it, we also have to copy activation actions and conditions, which are also deep copies. So this is really the meat of the copy that we're about to get to here. All right. Step 1. We want to iterate the new states. For each new state, we want to look up the old state. In the new to old table, we're going to assert that that lookup found a match, and then we're going to do the following little trick. There we go. So that gets the state pointer that goes with this new state. Then we're going to iterate the transitions of the old state. And for each of the transitions of the old state, we are going to copy it, right? So we need a new transition. The new transition has the following properties. Its parent state is the new state we were originally trying to fill. Its condition is, we need a way to copy it to condition. Opt condition copy. Arena the old transitions condition. Right? We need a way to copy an activation list. We already have that. Action list, copy action list. There it is. Arena, the transitions old activation list. The old transitions current activation list, really. And then finally we need to do a lookup again, so we'll use the same lookup structure, this time going from old to new. We're going to look up the old transitions destination state pointer and assert that that lookup found a match. And then again, we have to read that out. Why am I bothering? Old to new, and the new destination state comes out right there. And so finally the new transitions destination state can be the new destination state. Whew. Okay, so we're almost done. Now we just need to be able to copy this condition, and then we've done it. Transition case, opt copy condition, opt condition copy. Weird, I put copy as the first word on all my other copies, but not that one. Okay. Not quite that simple, because if the kind of condition we have is a condition set, we actually have to do some work. And what do you know? That's where the copy goes at the end. There we go. Perfect. Okay, so we now have a way to copy a model, right? Which is what we're going to do. So we're going to say, when we do this from now on, we're going to have gen contiguous is not actually going to operate on the context. It's going to get a scratch, and it's going to get a model. And probably it's also going to want the token. So arena, yeah, token kind says. We're going to give it the tokens, the model, and the file all separately. So there's the scratch for you. Here's the tokens. I believe that's like this, I think. Yeah. And here's the original model. And then what we can do is in this code right here, we immediately begin and a temporary memory section in the scratch so that we aren't modifying that memory permanently. We'll reuse that memory over and over again for each generation algorithm, and we will immediately copy the model. So we can do all of the optimizations we want on our own copy of the model. That'll all actually happen in that scratch memory, so that once we're done with the generation, all of the stuff we did can get thrown away. Now, if we get to a point where we want to use the same optimized model several times, what we'll probably want to do is reorganize a little bit and say, hey, this wants to live out here, and we'll have a thing that says, hey, do this low-level optimization and then generate these things off of it. But the reason we're not going to do that right away is because we're not sure if that's the way it's going to get organized. It might be that we never have to do two different things off of the same optimized model. You also have to remember that if that's actually happening, what that means is that we optimize two different things for two different outputs. The same exact optimization path worked. Now, it might be that we want to do that for speed purposes. Maybe this optimization is going to take so much time that doing it two different, slightly different ways for output speed is just not going to be worth it. But I have my doubts. I think it's more likely that we'll end up wanting to do different optimizations for every type of backend. So there we go. Now what we're looking at here is basically still nonsense. It's doing a little bit of work, which is checking if it's at the end, and then asserting that it didn't know what to do next. And then if it's not at the end, which it won't necessarily be, it will never increment and just run to completion after doing every single one of these ifs and returning an empty list, right? So it still does nothing, but we have a deep copy for the model now, and so our next job is going to be to split out those conditions that have end of files on them. So right here we're going to be able to start doing optimizations that are specific to the code we're trying to generate here. So in this code, what's going to be most important is splitting out those optimizations, or splitting out those cases where the condition contains an end of file, so that there are two transitions, one that does not contain the end of file and contains everything else, and one where the only input that can trigger that condition is an end of file. And then we'll reorder the transitions so that all of the things that happen at end of file are at the top and everything else is below that. And then we can do this more cleanly. Alright, so that's what's in store for the next episode. Thanks for hanging out for this one. We are going to start generating some better code in just an episode or two. Can't wait to see it. Hope you're along for the ride. Later. Bye-bye.